Hey everyone, and welcome. If you've ever looked at a complex 3D surface and wondered, how in the world do I find the highest peak or the lowest valley on that thing? Well, you have come to the right place. Today, we're going to master relative extrema in multivariable calculus. Let's dive right in. All right, here's our game plan for today. First, we're going to build up our intuition by just visualizing what these extrema actually look like. Then, we'll get our hands dirty with the math, finding critical points and using the super powerful second derivative test to figure out what they are. We'll lock it all in with a few solid examples, and then I'll leave you with a simple 3-step master plan to solve any of these problems. So think back to Calc 1, right? Finding a peak or a valley was all about finding where the slope, where the derivative, was 0. Well, guess what? We're using the exact same idea here in Calc 3. We're just leveling it up for 3 dimensions. Instead of a single derivative, we've got the gradient vector. And just like before, we're on the hunt for those special points where that entire vector goes to 0. It's the same core concept, just bigger.
Okay, first things first, let's build up some intuition. Before we even touch the math, what are we actually looking for on these 3D surfaces?
Yeah, so the ideas of peaks and valleys translate pretty much exactly how you'd think. A relative maximum, that's just the top of a hill. If you're standing at that point, the surface curves down in every single direction. And a relative minimum is the bottom of a valley. From there, the surface curves up everywhere you look. So far, so good? But here's where 3D gets really cool and kind of weird. We have this whole new character on the scene, the saddle point. And the name is just perfect, isn't it? Literally, picture a horse's saddle. If you move along the horse's spine, the saddle curves up. But if you move across it, where your legs go, it curves down. It's this conflict, curving up one way and down the other, that is the dead giveaway of a saddle point. Okay, so we know what they look like. But how do we actually find these maxima, minima, and saddle points with math? Well, the hunt always kicks off by identifying our candidates, which we call the critical points. And here's the official definition. A critical point is just any spot where the gradient vector is the 0 vector. Now remember what the gradient does, right? It points uphill in the direction of the steepest climb. So if that vector is 0, it means you're standing somewhere perfectly flat. There's no steepness, just like the very top of a hill or the very bottom of a valley. Now this is so important. For that gradient vector to be 0, it's not enough for one of the partial derivatives to be 0. Nope, both of them, f sub x and f sub y, have to be 0 at the exact same time. Seriously, this is probably the most common mistake on exams, so you gotta lock this one down. It has to be both. All right, we've got our list of suspects, our critical points. But now we have to figure out what they are. Are they a hill, a valley, or one of those weird saddle points? To do that, we need to bring in the big guns, the second derivative test. The absolute key to this whole test is this one special value we calculate. We call it the discriminant, or just D for short. And this single number, cooked up from all the second partial derivatives, is going to tell us everything we need to know. It holds the secret. And this table here is basically your cheat sheet. It lays out the whole decision process. The very first thing you do is look at the sign of D. See that third row? If D is negative, boom, you're done. It's a saddle point. Easy. Now, if D is positive, like in those top 2 rows, you know it's either a max or a min. So how do you tell the difference? You just take one more step and look at the sign of F double X. If it's negative, the surface is concave down, like a frown. That's a maximum. If it's positive, it's concave up, like a cup. That's your minimum. Okay, that's enough theory for now. Let's be real. The best way to get this stuff is to just do it. So let's dive into some examples and see how this all works from start to finish. We'll kick things off with this polynomial here. It's a nice, clean function, so we can really focus on the steps of the process without getting bogged down in any crazy algebra. Okay, so we just follow the plan. First, find the partial derivatives. Got them. Then, set them both to 0. Solving 2x plus 2 equals 0 gives us x equals -1, and 6y minus 12 equals 0 gives us y equals 2. So look at that. We've got our one and only critical point, -1, 2. Next up, we get our tools, the second partials, and we plug them into the formula for D, and out pops the number 12. So our D is 12. That's positive, right? That tells us it's either a max or a min. We glance over at f double x, which is 2. Since that's also positive, we have our answer. The point, -1, 2, is a relative minimum. All right, example number 2.
Now, take a look at this one. See how you've got a positive y squared but a negative x squared? That kind of opposing behavior is a classic clue that we might just have a saddle point on our hands.
And we just run the same playbook. Find the partials, set them to 0. That gives us our critical point at 1, 0. Then we calculate the second partials, plug them into our D formula, and what do we get this time? D equals -4. And because D is negative, we're done. That's it. We don't even have to check anything else. A negative discriminant is like a giant flashing sign that says saddle point. It's really that straightforward. Okay, last one. Let's tackle something a little juicier. See those cubic terms? That's a hint that things are about to get a little more complex. We're probably going to find more than just one critical point this time. And yep, there it is. When we set the partial with respect to x to 0, we get 2 answers, plus or minus 1. Same thing for y. So what does that mean? It means we have to check every single possible combination. You take an x, you take a y, which gives us a grand total of 4 candidate points we have to test. Now, when you have a bunch of points like this, here's a pro tip. Organize your work in a table. It's a lifesaver. You figure out the general formulas for D and F XX first. In our case, they're 36xy and 6x. Then it's just plug and chug. You test each of the 4 points and look at that. This one surface has the whole collection, a minimum, a maximum, and 2 saddle points. Pretty cool, right? All right, we've been through a lot, so let's just zoom out for a second and boil all of this down into a simple, step-by-step plan you can use on any of these problems, no matter what they throw at you. And here it is, your 3-step master plan. It never changes. Step 1, find your candidates. That's your first partial set to 0. Step 2, calculate your tools. That's your second partials and your D formula. And step 3, classify. Test every single candidate. You just find them, tool up, and classify them. If you can remember that, you are golden. And that's a wrap. You now have the full strategy for finding and classifying relative extrema. But think back to that table for a second. There was one case we kind of skipped over, wasn't there? What happens if D is exactly 0? Our test is inconclusive. It just fails. So what do you do then? What kind of weird, twisty surface could even cause that? That's a little something to chew on for next time. Thanks so much for joining me.